Hey there. So I'm very excited to move into the last chapter of the course, chapter 13, where we get to study a very powerful inferential technique called analysis of variance. Let's get started. All right, so section 13.1, just to actually introduce the concept of a one-way Anova, which is the acronym for analysis of variance. Okay, and so can you tell that I'm excited? This is just such an interesting application of statistics here. We learn inferential techniques for comparing three or more means. Okay, so far we've just tried to find out how confident can we be that certain samples are within the true population mean. Then we compared two separate means, and now we can actually compare multiple means, three or more. Many statistical applications in psychology, social science, business administration, the natural sciences, and so on involve several groups that you want to compare side by side by side. For example, an environmentalist is interested in knowing if the average amount of pollution varies in several bodies of water. A sociologist is interested in knowing if the amount of income a person earns varies according to his or her upbringing. A consumer looking for a new car might compare the average gas mileage of several models. So not just two things compared, several things compared. And so in this chapter, we will study the simplest form of analysis of variance, called single factor or one-way Anova. Okay, so Anova is analysis of variance. Okay, so a one-way Anova. Analysis of variance, that's an inferential method used to test the equality of three or more population means. So in other words, Anova, we will have that the null hypothesis is always that the means of the different populations are equal. So you could set that up as like mu1 equals mu2 equals mu3 equals ... however many different population means. Okay, and then the alternative hypothesis is just always going to be a statement that says at least one population mean is different from the others. Okay, and that's going to be the same setup for all of our one-way Anova tests. Okay, and if we end up rejecting the null hypothesis, this test doesn't tell us which mean might have been different. It just tells us that at least one of them is different. Okay, so it doesn't give us any more specifics than just saying that they're not all the same. Okay, the requirements to perform a one-way Anova are the following. There must be k simple random samples, and then one from each of k populations. Okay, or a randomized experiment with k separate treatments. Okay, so the k is kind of like the number of different categories or the number of different samples that you're comparing. The k samples are independent of each other, and so that means that subjects in one group cannot be related in any way to subjects in a second group. The populations are normally distributed. Okay, that's a requirement that we have for this one. The populations must have the same variance. Okay, so that is each treatment group has the population variance of sigma squared. And the factor is a categorical variable and the response is a numerical variable. Okay, so we'll get into some examples in the next section, but I just wanted to introduce the concept of this one-way Anova. And that's the end of this section right here, just an introduction. But I want to talk about this image right here where we see these different box plots. So box plots we've studied in the past, and it's a really good way of seeing where the data is kind of clustered. And then you can see that Q2, that little dotted line quartile in the middle where the median might be, or where you might think about where the mean might be. If we're comparing these three here, and if you think about the means would be somewhere clustered in the middle of these like interquartile range sections for these box plots. If H naught is true, okay, if the null hypothesis is true, so that would be a situation like in part A right here, then all the means are the same. And if there's any differences, you could attribute that just to random variation. So all the means are really, really close together, and any difference, you could just say that it's based on random variation. Okay, but if you have the spread of something like in part B, okay, that would be where the null hypothesis is not true. All the means are not the same, and the differences are just too large to be a result of random variation. Okay, so that's kind of the way that we would think about the one-way analysis of variance. All the means are close enough together where the differences could just be random variation. That would be if the null hypothesis is true. You would just have mu1 equals mu2 equals mu3, and they're not different enough for us to think that there's something else at play. Okay, so that's the introduction there. Nice short and sweet introduction. In section 13.1, we're going to start talking about a new type of distribution that we're going to use to study analysis of variance and use it in hypothesis tests.